Welcome back to my Smart Learning videos on science. This is for Year 9s in particular, for my lessons that the Year 9s are missing, but it's also useful for Year 7s. And it is a GCSE lesson, so it's good, suitable for Year 9s, 10s and 11s for their revision for their exams. So, last lesson we looked at just the different types of energy, and we looked at that energy can be in stores or energy transfers. This lesson, what I'm looking at is why can't something keep going forever? Why, if I move something, why doesn't it just keep moving forever and ever and ever? So this is known as the conservation of energy. Now, just to recap from our previous lesson, I've got a quick quiz for you to do. 5 questions. I'm calling it the recall quiz, like I did at school. I used to call it recall PT, progress testing, but I'm calling it recall quiz high 5. Right, because I'm going to give you a virtual high 5 if you get 5 out of 5, obviously. So, because we're not allowed to touch hands. So, quick question then from the last quiz, last lesson. What is energy? What is the definition of energy? If you just quickly write that down, I'll give you a second, press pause, write down the answer to that. What is energy? What is the definition of energy? Question 2. What is the correct word for movement energy? The correct scientific vocabulary for movement energy? If you press pause, write down the answer. Question 3. What type of energy do you gain if an object gets higher and higher and higher? What is the correct word for that type of energy? Press pause and write the answer down. Question 4. There are 2 types of energy. I've just mentioned at the beginning of this video. So if we categorize energy, we can put the forms of energy into 2 major categories. What are those 2 categories? And question 5, for my last lesson I was talking about my coffee. My hot coffee has energy. What type of energy is in my hot coffee? So if you press pause, make sure you check your 5 answers, make sure you've written them down, and we'll go through the answers now. So let's see if you got all 5 right. So what is energy? The definition of energy is the ability to do work. That's the actual definition. So energy is the ability to do work, and it's also work done is equal to, work done is energy transferred. The correct word for movement energy is kinetic energy. So kinetic energy is also known as movement energy, if any object moves. If something gets higher and higher, the type of energy gained is gravitational potential energy. So if an object gets higher and higher and higher, it gets gravitational potential energy. Number 4, 2 types of energy are energy stores and energy transfers. We've got energy stores and we have energy transfers. And the one that causes a little bit of confusion, hot coffee, what kind of energy has it got? Most people automatically go for, oh, it's got heat energy, but the heat energy is actually transferring from it. The hot coffee itself has a thermal energy store. So remember our 2 types of energy. There's energy store and there's an energy transfer. Now, from our last lesson, we talked about energy, but we didn't really talk about how energy changes or transfers from one form to another. So the way we do this though is we always write down the starting energy. It's like a story. The story always has a beginning, it has a middle, has an end. So the story starts off, where did the energy start from? What was it started with? Here, it's my torch, and my torch has got electricity or electrical energy. You always draw an arrow in the middle to show you where the energy is going or what's it becoming. That's the middle of my story. And the end of my story, it's been converted into light and heat energy. But I can't say it's a story, because with energy, there is no ending to the story. The story carries on forever and ever and ever and ever. It goes somewhere, okay? So, the electricity then. So if I've got 40 joules of energy there, if I've got 30 joules of heat energy here, where's the other bit? There must be some somewhere else, because 40 must equal 40 on this side. So if there's 30 joules of heat energy, there must be 10 joules of light energy. Whatever's, just like a mathematical equation, whatever's on the left must add up to whatever's on the right, because energy is what we call conserved, which I'll come on to now. So that's for my light bulb. So can you press pause on the video, but what I'd like you to do is for each of those objects, can you write down what are the energy transfers that have taken place in each of those systems, these energy systems. So if you press pause now, for each of those systems, write down the energy transfers. Now, if you've done that, what you should have then, for a burning match, the chemical store is the chemical energy store in the burning match. It's transferring into thermal energy, but it's heating, it's going out, and there's light energy. The torch, it's got chemical, it's a portable torch, it's got a battery inside, so it's got chemicals in there in the battery. You've got heat and light. The microphone, that's picking up my voice right now. The sound energy is coming from me, and it's going into the microphone. It's actually causing tiny movements in there should be actually kinetic energy in there, and that's being converted into electrical energy. The radio, obviously, is plugged in, it's got electrical energy, and you can hear a radio, it makes sound, but also the radio gets warm. A television has electrical energy going into it. You can hear the television, you can see the television, so there's sound and light, and there's also some heat coming off that screen as well. A catapult, you stretch it, it has elastic potential energy, it gets turned into kinetic energy with the projectile, and there's also some heating effect. A mobile phone then has the battery inside, has got a chemical store of energy in there. You can hear the mobile phone because there's little speakers in there, so there's sound energy. There's also some heating effect as well, and there's also some microwaves because it absorbs and it also emits some microwave radiation. A car then has chemical energy in its fuel, whether it's petrol or diesel, or it could be an electric car, so it can have a battery in there, so it will have a chemical store of energy. That turns into kinetic energy, it's the main form of energy. So the one that's underlined is the useful energy that we get from each of these systems. And for our car, you don't necessarily want to hear it, and you don't necessarily need it to get hot. So the ones that are underlined are the ones that we need, so the useful type of energy that we need. Now, what do I mean by the conservation of energy? Now, I'll come back to that actually. So, quick quiz then. What energy transfer is happening in a microphone, based on what we've just said? So, in a microphone, is it the green, red, blue, or yellow? Well, the answer is, in a microphone, the sound is coming from me and it's turning into electrical energy. So, for the microphone, it's the red. So, it's the sound into electrical energy. What about in a kettle? Well, a kettle, where is the energy wasted? Well, a kettle doesn't really give out light. A kettle doesn't have chemicals in there. But do you need to hear the kettle? No. So the kettle making a bubbling sound or whistling sound, that's a waste of energy. Now, weirdly, the heat energy is very important in a kettle because the heating element heats up the water and makes the water hot. However, some of that heat energy is actually wasted because it goes out into the environment. Now, that's not the energy, you want that heat to be in the water, not in the environment. So some of that heat is actually wasted, but most of it is useful. So, when we draw energy diagrams, you always draw the starting off energy on the left, and you do the energy it's been turned into on the right. But you always write the useful energy first, and the wasted energy after. So, conservation of energy. What do I mean by the conservation of energy? Energy cannot be created or destroyed. It's just transferred from one form to another. So it's just transferred from one form to another. So it keeps changing from one thing to another thing to another thing to another thing. Okay? And eventually it just keeps spreading out and spreading out and spreading out and spreading out. So we call that word dissipation. So energy becomes more spread out and less useful or less easy to use, and therefore we call this dissipation because the energy just keeps constantly spreading out and becoming less and less and less and less. So that word is known as dissipation. So here is a table again. If you press pause after drawing the table, see if you can fill in the table and write in what things are useful energy from them and what things are wasted energy from them. So, if you pause now to go at that, the types of useful energy from a TV, well, what do I want from a TV? I want to hear it, I want to see it. So it will be light energy, and sound energy, but the wasted energy from my TV is heat energy. I don't use my TV to warm up my living room. Your electric kettle, well, the useful energy, it's electrical energy going into it, but the useful energy is the heat energy that goes into my kettle to warm my water up. However, the wasted energy, I don't hear it, so it's sound energy. Some of the heat energy is also wasted because it goes out into the environment. I don't use the kettle to warm up my kitchen. Headphones then, the useful energy, electrical energy is actually going into it, but the useful energy from my headphones is the sound energy because I want to hear it. But the vibrations, there's tiny kinetic energy in there as well, but the vibrations are causing some heating effect. So a lot of the time, wasted energy, a lot of the time is heat energy. So it's heating up the surroundings where you don't actually need to heat up the surroundings. So another little activity to have a go out trying to draw energy flow diagrams for these particular questions, and see if you can make sure you write the useful energy and the wasted energy for each of these. Press pause and have a go. Now, coming back to that previous question about in our objectives, can something keep going on forever and ever and ever and ever? Well, why doesn't a pendulum or a pirate ship at Drayton Manor or Alton Towers, why don't they keep swinging forever and ever and ever? Why does a pendulum not just keep going forever and ever? Because if I got one now and I was swinging it, eventually would come to a complete stop. Well, energy spread. Remember we said energy cannot be created, it can't be destroyed. If this was a perfect system, this would keep going forever and ever and ever. So for instance, if I raise my pendulum from the bottom and I lifted it up to the top as high as I can go, I'm going to lift it higher so it's going to gain gravitational potential energy. So let's just say it's got 100 joules of gravitational potential energy here. Now unfortunately I'd usually annotate all over this and write the numbers and things so you can see it, but as I can't use my classroom at the moment because we have to all self-isolate, I can't write all over my TV. So what I would do is I would lift this up here. This would be 100 joules of gravitational potential energy. And as I let it go, the pendulum will start to swing. And as it swings down, the gravitational potential energy is turning into kinetic energy. And as it moves, it's got kinetic energy. And then as it goes to the bottom, it has got its maximum kinetic energy, but it's got its minimum gravitational potential energy because it's got to its lowest point. Now remember, GPE, gravitational potential energy, gets more the higher it goes. So if it's at the bottom, if it's at its lowest point, it's going to have 0 gravitational potential energy, but its maximum, because that's the bit where it's going the fastest, because if you think about riding a pirate ship, when you get to the top, you kind of stop for a split second, and if you're not moving, that means you've got no KE, you've got no kinetic energy, but you've got the maximum gravitational potential energy because you're at the highest point. And if you let go, you start to swing again and you get faster, 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 faster. And kinetic energy, the most kinetic energy you're going to have is the fastest you're going. So the fastest is going to be at the bottom here. So you're going to have the maximum KE. So if I use some numbers then, so if I say let's have got 100 GPE and I've stopped there because I'm holding it, it's going to have 0 KE because it's not moving. And just like if you're on a swing, if you get to the top and you stop, you've got 0 KE, you've got 100 GPE. And as I swing lower and lower, if I go halfway, I'm going to have 50 KE and 50 GPE. They've interchanged. My gravitational potential energy has been transferred into the kinetic energy store of that pendulum. So as it goes to the midpoint there, 50 GPE and 50 KE. As it gets to this point here, I'm going to have 0 GPE because I'm at the lowest point and I've transferred all my gravitational potential energy store. It's been transferred into the kinetic energy store. So here I've got 100 KE and 0 GPE. And as it moves up, it's got its fastest here. That means anything here is going to be getting slower. So here it's losing its GPE, or it's transferring its GPE, or it's gaining GPE. It's gaining GPE, but transferring it, it's losing its KE. So the KE is going into the GPE. So at that midpoint there, I'm going to get 50 KE and 50 GPE, same as what it was there. And then as it gets right back to the top point there, it's going to get 100 GPE. It's got the maximum GPE again, but it's stopped for a split second, so it's got no kinetic energy, so it's got 0 KE. And then, because it's stopped for a split second, and then again and again and again, and it'll just keep doing that. So 100 GPE, 0 KE, 50-50 because they've interchanged. Here will be 0 GPE, 100 KE, back to here, 50-50, and then up to the top again, we'll get our maximum GPE, and you got your 0 KE because you stopped. And obviously you can do like quarter amount, so let's say here it'll be 75 GPE, 25 KE, 50-50. It'll be here, down here, it will be 75 KE, 25 GPE, and then 100 KE and 0 GPE. So, but why doesn't it carry on going forever? If it did, we'd call this something called perpetual motion. Something, if I get like a spinning top and I spin it, it just carry on spinning forever and ever and ever and ever and ever and ever and ever. Never stop. Now, in space, that might be possible. If I've got something to spin, it'll just carry on spinning without stopping ever. But why would a spinning top stop on Earth? And why would this pendulum eventually stop? Well, the energy is being dissipated. It's being spread out. So there are other energy transfers that are happening here. This pendulum, and even pirate ship, will have somewhere where it's attached to. And where it's attached, there's going to be some rubbing on the two surfaces, which is causing friction. And that friction has a rubbing effect, and that has a heating effect. So energy is being dissipated. So not all of that energy is going into kinetic energy, some of it's going into the heating effect. As the pendulum's swinging through the air, as it's cutting through the air, there's some rubbing with the air, that's air resistance, and that causes a heating effect too. You might be even to hear it, you might make a shoo, shoo sound, or vroom, vroom sound. That is some of the sound energy that's been dissipated into the environment as well. So not all of the energy is being spread throughout the transferred into this system. Some of it's being dissipated elsewhere. So that's why, answering our question, why don't things transfer energy forever and ever and ever and ever? Why can't it just keep going on forever and ever and ever? Because energy is being dissipated. But energy is always being transferred from one form to another. That is the conservation of energy. And how is that energy wasted, like we just said? The useful energy here is the GPE and the KE, because we need that. The energy of this system has been wasted because of the friction and the air resistance. Most often than not, in most systems, the energy is wasted as heat energy. So how could we reduce that heating effect? How could we reduce the energy being wasted so more of it is going into our system that we need? Well, we want to reduce that friction because it's the friction that's causing the problem. So what can we use to reduce friction? Some kind of lubrication. So any kind of oil or some other kind of lubricant that makes it have less friction will make it swing more freely, and therefore will make this a more efficient system. And that's what we'll go on to next time. We're going to look at efficiency, about how wasted energy and useful energy, how we can make our systems have more of the useful energy and less of the wasted energy. And one of the major things that causes, and especially machines and other kind of systems, is the friction that happens when two surfaces rub together, and that causes a heating effect, and that heating effect dissipates to the surroundings, and you are wasting some of that energy. Okay, but remember, the learning objective for this lesson: energy, you can't create it, you can't make it out of nothing, you can't destroy it, it can't just disappear. It can only transfer from one form to another. And some of the energy is wasted, but it's dissipating into the surroundings. So if that's been useful, please like, watch, subscribe, share. The more people that don't miss out on the learning, the better it'll be for everyone. So thanks for watching, and I'll see you on the next video, and look after yourselves.